Leibovich. Part of the introduction. The purpose of this lab is to demonstrate Newton's second law and the momentum principle. The momentum principle is essentially that force is equal to change in momentum over time. Newton's second law is essentially force equals mass times acceleration. Intro to models and details of the experiment. On the left, I utilize tracker to track the position over time of me dropping a paper ball, and I selected the point of mass, gave it a reference of scale, and aligned it with the axes. On the right, I used GlowScript and I modeled the position versus time graph. Assumption. At first, we assumed that drag force is equal to 0, and then drag force is equal to negative b times velocity squared. So another part of the introduction is the main fundamental physical principles. Final velocity is equal to initial velocity plus F net over mass times delta t. We also know that final position is equal to initial position plus velocity times delta t. We know that weight equals mass times gravity, and we know that drag force is equal to v times velocity squared, and we also know that F net is equal to weight, or force of gravity plus drag force. This is a brief preview of the main results. This preview shows that Newton's first, second law, and momentum principles were proven to be true. This graph has three curves: the experimental, the model with the drag, and the model without the drag. So the system is the paper ball. Surroundings is everything around it: the carpet, the ruler, the wall, and etc. So initial conditions. Initial conditions is that drag force is initially equal to 0, so initially force is just equal to W, which is just mg. The paper ball is not moving yet, and time is equal to 0. So in terms of the coding, here I estimated proportionality constant for the magnitude of the drag force. This took a couple of attempts, and then at some point I was able to align both the experimental model and the model with the one I created on GlowScript, and I aligned them and I was able to estimate the proportionality constant. The next is the time aspect, which is it took 0.534 seconds for the ball to drop and hit the ground. Here are the fundamental principles that we are aware of: that weight is equal to mass times gravity, and then drag force times j hat, and then drag force is equal to b, the proportionality constant, times the velocity, and then we know that F net is equal to weight plus drag force. Here we have the velocity update formula, and then we have the position update formula. So overall, similarities and differences between data sets and model predictions. So we can see that the model with the drag and the model without the drag expected to hit the ground faster than the actual experimental model, and we see that the model without the drag actually expected to hit the ground the fastest. This is what this demonstrates. So potential sources of error. So there could have been several potential sources of an error: implying the ball's mass point and obtaining the position versus time graph. Also video camera slightly moving, human errors, plotting scale, the proportionality constant might not be exactly accurate, and the graphs might not be completely aligned or not proper. So examining velocity versus time predicted by my models without the drag. Which model predicts a terminal velocity? So the model with the drag predicts a terminal velocity because at a certain point the drag force will equal to net force, right? And this is also when the net force is equal to 0, and then at this point there will be a terminal velocity, and this is evident in the model with the drag. So what if imagine that the object is initially turned downward? Would the terminal velocity in this case be same or different in the case of the object was initially dropped from rest? So the terminal velocities should be the same because the drag force is proportional to velocity squared. So at some point the net force will also be equal to 0, and at that point, they will also have a terminal velocity, and this terminal velocity would and should be equivalent. Thank you for listening. My name is Ivan Nikolovich.